Well, today's a great day because we're going to be doing calculus. What? What? Wait, we're doing calculus in a calculus class? Yeah, it's true. We've been spending a lot of time building up our understanding of geometry, which is important because calculus is built on a foundation of geometry. Now that we've done that, we can start dipping our toes into the waters of calculus. And we're going to do it today by looking at a very special topic, which is what we call parametric curves. So what are they? Well, you can imagine that there's this particle moving through space. And what we're going to do is keep track of the particle. Well, as it moves through space, it traces out a curve. And we call that a parametric curve. The parameter refers to time. Where are we at any given time? Now, of course, since we're moving, we're changing, and we can start to ask questions such as, what can we say about the change? Great calculus question. Well, let's get going. So what's our picture we have in mind? We have some curve moving through space, and it's doing all sorts of things. It can move around in all sorts of ways. And what we think of happening is that there's some parameter time. So we have our particle. Maybe our particle is here. And we say, all right, we can describe its location at a given time by saying, well, where are you at for x, where are you at for y, and where are you at for z? And there we go. You give us a time, we give you a location, and we all agree. And as time varies, we just change the coordinates, our location varies. So we can keep track of everything. So, great, wonderful. Well, let's start doing calculus, you say. Well, hold on. There's a small catch. If you ever want to do calculus, you have to be able to do two things, and only two things. And those two things are, you have to be able to add, you have to be able to scale. Well, you can't add points. They just don't work because those are dependent on your coordinate system, and you can't, it doesn't make sense. And you can't really scale either for the same reason. So, if you can't add and you can't scale, what do you do? Well, what you do is you say, well, let's not do it where we think of it as a point. Let's change it to an object where we can add and we can scale. And how do we do that? Well, what we do is we say, we're not going to think of it now as a point. We're going to switch to a vector. So we take our vector where we nail one end down to the origin and the other end points to our current location. And that vector is very simple to figure out because we know the two ends. There's the point and the origin, and therefore our vector x, t, y, t, z, t. And like, oh, so you went from like these rounded things on the ends to these angled things on the end. Yes, we did. And does it help? It does, because vectors, you can add and you can scale. So we can do calculus. So that's good. And what's happening here? Well, you can imagine that as your particle moves, what you're doing is the vector just keeps pointing to where you're currently at. So the vector points to your current location. All right, now we have something we can actually do calculus with in terms of our parametric curve. So what's our next step? Well, the first step in doing calculus is we have to talk a little bit about limits. Now, just a little bit. We're not going to go into too much detail, but just enough to sort of remind ourselves what's happening. Now, there's the intuitive thing about limits. Limits say what should happen. So, in other words, we might have a problem saying what does happen at a particular location. So limits say, well, don't worry about what does happen. What should happen? And the way we figure out what should happen is we say, well, what's happening nearby? What happens as we get close? So if you go back to the technical definition, and I want to preface this by saying, we're not going to push too hard with the technical definition of limits. This is about almost the only time we're going to talk about it. But it's just nice to say, hey, things translate in a good way. So go back to our single variable calculus functions. You know, the limits that we all know and love. These are also called scalar. So scalar valued just says that we have a function whose output is a number. A vector valued means a function whose output is a vector. So that's why we're switching from outputs to numbers, outputs to vectors. So we can actually compare. So we have a function, and we want to say the limit of that function is some number. Now, in vector valued, we have some function which is outputs are vectors, the limit is some vector. All right. What needs to be true? Well, we have to cue off of this close. What does close mean? Well, there's sort of two ways to be close. There's the inputs being close, there's the outputs being close. So we have sort of two measurements of distance. So one measurement is for the output. We call that our epsilon. So here we say, look, if for each epsilon greater than 0, same thing, each epsilon greater than 0. Then there is a delta greater than 0. Okay, same thing. So what are epsilon and delta? Epsilon is a measurement of the outputs being close. Delta is a measurement for the inputs being close. We are told, look, we have to be a certain amount of closeness in the output. And so our goal is, let's be a certain amount of closeness in the input to guarantee that. So that's what the following things say. The absolute value of f of t minus L, that's the distance between the function and the limit. So that means that how far apart they are is less than epsilon. Look, it translates, right? The absolute value is a measurement of distance. Magnitude is also a measurement of distance. So we have the function and the limit are close. That's what we want. Now, we need to also have that the inputs are sufficiently close. So again, it translates exactly as we want. In other words, limits do what we think they should do. Now here's the important takeaway for limits. How do we know if vectors are close? Well, intuitively, it should be that two vectors are close together if they're close in every individual entry. And so we say, okay, what we need to focus on is what happens entry by entry. Well, we see why that should be true. And here's sort of an argument. I'll do an example just to sort of emphasize it. So let's suppose we're in 3 dimensions. And what can we say? So if I have two vectors, say A1, A2, A3, and I want to look at how far apart they are, well, that just says take the difference between them and take the magnitude. Well, that is, if you apply the magnitude formula, that's A1 minus B1 squared, A2 minus B2 squared, and A3 minus B3 squared. Right? So far, so good. Now, here's the thing. Let's just say, look, suppose I want to compare just the first entry. Well, look, if I drop those two, what happens? Well, I've only made the whole thing smaller, right? If I drop those, I made it smaller. So it's bigger than or equal to the square root of A1 minus B1 squared, which is, you can just say A1 minus B1. What's happening here? What is this saying? Well, it says that a measurement of how close these vectors are is bounded below by how close they are in the first entry. Same argument, though. It's how close it's bounded below by how close they are in the second entry. It's bounded below by how close they are in the third entry. So if some entry of these pair of vectors is not close, then the two vectors can't be close. So that's what's happening. So we know if two vectors are close, they have to be close simultaneously in all the entries. And now you say, well, look, that just says we only have to work entry by entry by entry, because if we have something converging, things have to work entry-wise. That's going to be a huge theme for us. And indeed, that's going to be our basically our big idea. So let's talk about derivatives. Now that we can do limits, we can do derivatives. So we have our vector valued function, and so each individual entry is its own function. And we say, okay, we'll take the derivative. Well, we need to be able to add. That's what's happening in the numerator. So f of t plus h minus f of t, that's the version of adding. We need to be able to scale. So that's what's happening when we divide by this factor of b. Now you might say, why are you choosing b? Well, we already have h showing up somewhere, so we don't want to use h in two different ways. That's why we're choosing b. It's just a symbol. All right, we say, okay, well, look, we know how to add and scale vectors. We do it entry-wise. So we do it for every individual entry. Okay, and now we say, look, limits work entry-wise. So instead of taking the limit of everything, we take the limit of every individual entry. And now we say, but wait, now it's just back to where we were before. These are single variable functions, and we know what these limits are. They're the individual derivatives. And therefore, when we're taking derivatives of vector valued functions, entry by entry, that's how we do it. Which means that our rules generalize in the right way. We say, look, since everything works entry by entry, then what we can do is apply all the old rules from before. For instance, the sum rule works. And what does that mean? Well, it says if I want to take a derivative of two vector valued functions, being added together, take the derivative of each one separately and add the results. In a similar way, we can multiply by a constant when it says, look, if I have a constant times a vector valued function, take the derivative of the vector valued function and multiply by the constant, just as we did before, which is great. We also have a chain rule. Suppose I have a vector valued function g plugged into some, sorry, let me back up. I said vector value, I meant to say scalar valued. So g, input is a number, output is a number, and then I plug that into a vector valued function. And I ask, well, what's the derivative? Well, the moral is I look at every individual entry. And if it's the case that in every individual entry rule works, then the rule works in general. And it does. We say, look, apply the chain rule entry by entry, and then each entry has this g prime of t, and it comes out. So everything works. Even the product rule. And the product rule, you might say, well, wait, which product rule, right? Because there are three different products that come up with vector valued functions. There's what's called the scalar product when you have a number times a vector. There's the dot product when you have two vectors which dot together. And there's the cross product. And the moral is they all work. They all do exactly what you think they should do. Derivative of the first times the second plus the first times the derivative of the second in every single case. And therefore, derivatives in some sense are nice. We don't really have to learn a lot of new tools. Indeed, it's really more just saying, hey, let's take our old tools and apply them one entry at a time. So, life is good. Well, now that we can do derivatives, we can start talking about things such as tangent lines. Well, what do we mean by that? Well, let's suppose we have some vector valued function, so we'll just make one up here. And so there's our vector valued function. And we have a point that we're interested in. We say, okay, there's our point. And we want to know what's the behavior of that function near that point. Now, what can we do? Well, we do what we always do, which is we say, let's look closer. In calculus, a big theme is, hey, zoom in and see what's happening. And so we do our traditional, okay, we pick this up and we zoom in, and what happens? Well, what happens is that we have our curve. We see it's a much simpler curve. It's still not completely straight, but all this sort of bendiness that happens far away, we don't really worry about, because we don't need to worry about what happens nearby. That's the idea of calculus. Say, okay, well, can we do better? Yeah, we zoom in a lot more. I mean, we zoom in really, really close. Okay, so we zoom in really, really close. And as we've zoomed in really close, what happens is that we've started to straighten out. And so much so that we can't even tell that there's any curve at all if we zoomed in very, very far. Now, we say, okay, we say, aha, once we zoomed in close enough, we say, that looks like a line. Okay, great. So, what's that line? So, we call that line the tangent line. And now we're after a line. Well, how do we find a line? Well, whenever we find a line, it doesn't matter what line it is, we always say, look, we need two pieces of information. We need a point and a slope. All right, well, point, easy. That's the location. And so if we have this parametric curve, we'll call it R of t. We look, just plug in the t value. That's our location. Life is good. What about our direction? Okay, so how do we handle direction? Direction being the new form of slope. Well, we think about, okay, if I want to find a direction, what we can do is we take our point. See this right here, this is at time t. We move just a little bit. So this is at t plus h. So we've moved just a little bit out. And we say, okay, let's look at this vector right here. It's a reasonable vector to do. And if we look at it, we say, okay, well, that vector looks like just entry by entry, right? So it's x t plus h minus x of t, comma, y of t plus h minus y of t, comma, z of t plus h minus z of t. So you just take the difference in each entry. And now we say, okay, if you divide by h, that just sort of helps it scale, because otherwise if you don't divide by h, and you let it get closer and closer and closer, it says, oh, it's going to become a zero vector. Dividing by h scales out so that it doesn't go to zero necessarily. And now we say, whoa, hey, look, what's happening? In each entry, it becomes a derivative as h goes to zero. So this is x prime of t, y prime of t, and z prime of t as h goes to zero. And so that's why what's happening is that the vector r prime, x prime, y prime, z prime, that's giving us our direction to go. It actually makes sense if we think about sort of the intuition, because what is x prime telling us? X prime tells us how we change in the x direction, y prime, how we change in the y direction, and z prime, how we change in the z direction. And when we think about the direction vector, it should be saying, well, how are we changing? How do we move? So that's good. So now we have our point, we have our direction, we can find our lines, and life is good. Okay, one last piece for today. And it's this good fact that we're going to use. So, suppose that we have r of t, it's a vector valued function, it has constant magnitude. Then r of t and r prime of t are orthogonal. Now, what does this mean? Well, let's think about it. We want to show two things are orthogonal. How do you show things are orthogonal? And the answer is dot product. Dot product is the way you show two things are orthogonal. So we can even see our goal. Our goal says we want to show r of t dot r prime of t equals 0. All right, well, how do we get there? Well, what do we have? Well, we're given that r of t has constant magnitude. So we know that the magnitude of r of t is equal to some constant k. So we want to show that the dot products are 0. We're given that the magnitude is a constant. And we start to say, well, how are these things related? Well, we're going to do a little subtle thing here and say, well, look, I can square both sides. And the magnitude of r of t squared is k squared. Now, you might think, okay, sure, why not? Well, how do you find the magnitude of r of t squared? It's r of t dot r of t. That's one of the nice features about the dot product. In fact, that's sort of how we got into our geometrical interpretation of the dot product. It says, oh, there's some connection to magnitude in dot product. And now we say, okay, great. Well, we see a derivative there. Let's take a derivative of both sides. So, one side is easy to take a derivative of, namely the derivative of k squared. The derivative of that is 0. Okay, how about this side? Well, what do we need to do? It's a product rule, because we have a dot product, and so, okay, do the product rule. Derivative of the first dot the second plus the first dot the derivative of the second. Okay, so there's our product rule. And now we say, oh wait, dot product, it doesn't matter which order we do things in, and therefore, what can we do is we can say that this side becomes 2 times r of t dot r prime of t, and it's equal to 0, and divide by 2, r of t dot r prime of t equals 0. All right, well, why is this interesting? Okay, so you might imagine the following scenario. So let's suppose we have a sphere. So here's a sphere, and what can we do with it? Well, imagine that you lived on the sphere. You know, there are some people who believe that we live on a sphere. We call it the Earth. And it's a good belief. I support it personally. So what's true? Well, you can imagine that you travel on the surface of the sphere. So as you move along the sphere, what's happening is you are moving. But let's imagine we put our origin at the center. Because we're on the surface, what can we say about the magnitude of our position at any given time? What's the magnitude of r of t? Well, the answer is it's the radius of the sphere on which you stand. So this motion on the surface of the sphere is always going to have constant magnitude, which means that when we look at the tangent lines, they're always going to be perpendicular. So how does that translate into the sphere? Well, it says that the tangent line at any given point is actually going to just be perpendicular to the sphere. So if this is our tangent line to r of t, it doesn't matter where we're at, it's always going to be perpendicular to the sphere. And that's the idea. And we'll use this idea in the near future when we talk about some various decompositions of acceleration. But of course, that's to come, right, for another day. But for now, we should go and do some practice. So, see you soon.